the geodesic into the infinite future or all the way back to the Big Bang. It's defined for all past and future times independently of the ball. Geodesics generally don't just end, except at singularities.
Alright, so what he's saying is, if you never had any resistance whatsoever, and you just took something and threw it, it would either go to the beginning or the end of everything. There's nothing to hinder its progress, and that's a geodesic.
In fact, in general relativity, singularities are defined as the endpoints of geodesics.
Okay.
All geodesics in the universe come together and terminate at the Big Bang. We call the Big Bang a past space-like singularity because it occupies all space in the past. A black hole contains a future space-like singularity, which means that all geodesics within a black hole space-time end at the singularity in the future.
Why are you staring at me?
No, that doesn't mean that you are doomed to be
Jasper.
crushed by a black hole. I mean, you might, but you might not.
Huh.
The black hole singularity is the all-encompassing future for the space-time that lives beneath the event horizon, in the same way that the Big Bang is the encompassing past for the outside universe.
They're just the
So
opposites.
the black hole and the Big Bang singularities are starting to look more alike, with the difference being their residence in the future versus the past, and the fact that black holes are embedded within a greater universe, while the Big Bang is the entire universe. How do we make a black hole look more like a universe? We'll need
You
to
know what this is
make-
reminding me of now? Like a choose your own adventure. There's a beginning. There's always a beginning. But there's different endings. And it's almost like we're all on a time path towards different endings, right? We could end up in this black hole, this black hole, this black hole, but one day we came out of the Big Bang and we're going to a black hole one way or the other. I think that's kind of what he's saying.
Black hole interior mathematically indistinguishable from a universe for somebody inside that black hole. The first step is to send that singularity to the past. A time-reversed black hole is easy enough. It's a white hole. And it's a valid solution to the Einstein equations. Naturally, we've discussed these before. The past space-like singularity of the white hole is surrounded by an event horizon that is the opposite to the black hole event horizon. It can only be crossed from the inside to the outside. Space flows at the speed of light across the event horizon from within. That's starting to look like our universe. A past space-like singularity and an event horizon that can't be crossed from the outside.
So, yeah. Huh.
There still is an outside in which the white hole just appears as a bright but localized point in space. The outside region doesn't share the same singularity origin as the white hole.
So, wow. We're talking about time travel. We're talking about maybe those are new entry points into the universe from alternate dimensions. Maybe those are new entry points from a time traveler that cut through the dimensional barriers to re-enter our Big Bang universe at different points in time, and they made white hole entries. Wow, this is interesting. It's very fascinating.
On the other hand, anyone inside the white hole wouldn't know that. So could they be fooled into thinking that they are in a regular universe? At first glance, despite the similarities, the interior of the white hole looks nothing like our universe. Now, the white hole was discovered by messing around with the coordinates of the OG black hole solution by Carl Schwarzschild. The same trick gave us wormholes and mirror universes, and we mapped those weird spaces in a previous episode. The interior of this type of white hole looks nothing like our universe. For one thing, it's made of pure space-time, no matter included.
No
And
matter.
it's highly inhomogeneous. The curvature changes dramatically as you approach its singularity. But our universe appears to be highly homogeneous. Matter and energy are very evenly spread out, and it was even more evenly spread out in the early universe, and the space-time curvature is nearly flat, so no crazy tidal forces like in a white or black hole. The space-time of our universe is well described by the Friedman-Lemaitre-Robertson-Walker metric, which we also talked about in the Center of the Universe episode. But there's actually a way to fit an FLRW metric inside a black or white hole, so those inside couldn't tell the difference. The first realistic mathematical description of a black hole formation was discovered in 1939 by Robert Oppenheimer of atomic bomb fame, along with his student Hartland Snyder. They approximated the collapse of a star by modelling it as a spherical cloud of matter with a perfectly homogeneous density and zero pressure. The thing collapses under its own gravity and an event horizon forms around it. But within the collapsing cloud, the matter remains homogeneous and the spacetime is flat until it becomes a singularity. Now, real stars don't look like this. They get denser towards the centre and have plenty of pressure. But the Oppenheimer-Snyder solution gave our first insights into black hole formation. And it also showed another weird property. This assumption of homogeneity and zero pressure was the same assumption that Alexander Friedmann made when he first solved the Einstein equations for the whole universe. And it's the assumption behind the FLRW metric. In fact, you can describe the spacetime of a collapsing star by patching one of these FLRW metrics inside a Schwarzschild metric for a black hole. And that's true even after the black hole's event horizon forms. So you can have what looks like a black hole from the outside, but looks like comfortably flat space inside the still collapsing star. If it works for the black hole, then it should work for the white hole. Just flip the time axis and you have a white hole containing a bubble of expanding space that looks much like our universe.
So all he's saying is it could all be exactly the same thing. The black hole, the white hole, our Big Bang universe could all exactly be the same thing, but it just looks different depending on where you are in your perspective. So it looks like, oh, white holes are different from black holes, and we're different, but we're not. We're all the same. Everything's exactly the same. Maybe we are inside a black hole. Maybe it's all one. Like I said, maybe these white holes are entry points into our universe, and once you leave the parallel universe or the other universe, it destroys it, and therefore that's why there's no evidence of any matter inside those white holes, and it's all just one continuous thing moving all together.
If such a white hole was big enough, it could look exactly like our universe. This was the basic proposal by Indian physicist Raj Patria in his black hole cosmology hypothesis back in 1972. As far as I've been able to tell, no one has convincingly shown that this can't be true. There's also the idea that universes are born as white holes produced after the collapse of a black hole. That's Cosmological Natural Selection by Lee Smolin, and yeah, we did an episode. In that case, black holes don't form singularities but rather bounce back outward to create new spacetimes from the resulting white hole, which itself creates new black holes, etc. Okay,
Endless.
So we need one last ingredient to be able to answer maybe to the question that we started with. Are we in a black hole? In 1999, Stephen Hawking showed that if a black hole is leaking its mass via Hawking radiation in perfect equilibrium with the radiation that it absorbs, for example from the cosmic microwave background, then the line between the white hole and the black hole becomes unclear. They could be the same object. If you lump all of this together, a very specific construction for white holes to make them look like our universe from within, and Hawking's argument that equates white holes with black holes, then there's a roundabout way to argue that we might not be in a black hole. So is the universe a black hole or a white hole? Well, probably not, but not absolutely not. There's no good reason to believe that this is the case, and so we shouldn't believe that the universe is a black hole. We need some deeper explanatory value to this hypothesis to really take it seriously. Cosmological natural selection might be a path to that, but we also need some evidence for that in order to proceed. However, if we are in a black hole, then there is a huge upside. We now know what the interior of a black hole looks like. It looks like this. And there are indeed libraries in this black hole. Perhaps one day one of the books in these libraries will also answer the next question. If we're within the event horizon of a black/white hole, what's on the outside? Maybe a universe inhabited by people asking the same question with the same answer, that they are in a black hole, and so on ad infinitum in a series of black holes forming an infinitely nested spacetime.
Wow. Fascinating. All this stuff is fascinating. You know, I haven't thought about this kind of stuff in a very long time, but yeah, pretty fascinating to try to think about it. And crazy how they, over the years, they keep piecing this stuff together with math and stuff. Like, wow. So Matt will return in 2 weeks when he finds the right white hole to return to our universe. That's pretty good. All right, I would say, so here's the thing. This is completely different from any kind of React stuff I've done up to now. Fascinating stuff. I like thinking about the big picture stuff. Not to say that it really affects our daily lives, but it's always good to kind of think about it in perspective to everything else around us. And it was nice. It was cool to hypothesize here for about a half an hour about this stuff. I hope you enjoyed it. Hope the volume levels were good. I don't know why my Xbox tried to prevent us from doing this. But anyway, thanks for your support, and I hope you enjoyed the video. Awesome.